Alright, so in this video we're starting a new section, section 2.6, and that has to do with limits and infinity. And so we dealt with infinity a little bit in the previous section on limits. For example, we took a look to see what would happen, for example, if x approaches a, if f of x is equal to plus or minus infinity. Remember, in this situation, then we said that x equals a is going to be a vertical asymptote, so the function typically does something like that. Okay, what we want to do now is we're extending this definition, so now the infinity is going to be down here, and then we're going to see what f of x does. So before we do that algebraically, let's take a look to see geometrically what this is doing. And so here's my x and my y. And now as x goes to positive infinity, that means you're looking to see what happens as your x gets larger and larger and larger, right? And so for the limit to exist, that must mean that the function is kind of settling down out here into a single number, right? It could oscillate or something through here. Or it could even have a vertical asymptote somewhere in here, right? Because all we're interested in is what's happening out here. Okay, so this is what it would look like if f of x had a limit as x goes to infinity. And in fact, this is also called a horizontal asymptote. Horizontal asymptote. And so let's go ahead and define that more formally now, and that is definition. The line y equals k, that's the horizontal line, is a horizontal asymptote for f of x if the limit as x approaches infinity of f of x equals k, or the limit as x approaches minus infinity of f of x equals k. Okay, so you could come into at either direction. Okay, so there's some functions that we know that have horizontal asymptotes. So for example, do you recognize this function? Maybe not. I was trying to write 1 over x. Yeah, if we take the limit as x goes to infinity of 1 over x, right, what happens is the denominator is getting bigger and bigger. For example, 10, 100, 1000, and so the function 1 over x becomes 1/10, 1 over 100, 1 over 1000, and so these numbers are going to 0 as x goes to infinity. And so we would say that y equals 0 is a horizontal asymptote for f of x. Good. And by the way, you see that the limit as x goes to minus infinity of f of x in this case is also equal to 0. So you actually get the horizontal asymptote going in both directions. Good. What other functions do we know have a horizontal asymptote? Well, how about this function? Does this look like a familiar function? This is e to the x power. So if we take the limit as x goes to, oops, I'm sorry, I got that wrong. It's e to the minus x power. As x goes to infinity of e to the minus x. You could think of it as taking x to infinity of 1 over e to the x, right? That may be easier to think about. So then as x goes to infinity, e to the x goes to infinity in the denominator, so overall the fraction is going to 0. Okay, so here y equals 0 is a horizontal asymptote. Good. Alright. Now, do you know of any functions that have other horizontal asymptotes? Well, we could construct one, but I want to take a look at the tangent function first. the tangent function, I'm going to restrict my attention to the graph between plus or minus pi over 2. And so then the graph comes down like this. Whoops, sorry about that. That goes through the origin. Now this function is 1 to 1, and so we can invert it. And so if we do the inversion, remember how we did that? We reflect across the line y equals x. Oops, this kind of comes up a little bit more. Oh well, you'll have to imagine that a little bit. Okay, and so what happens is that vertical asymptotes of the original function become horizontal asymptotes of the inverse. And so the inverse tangent function, let me write that so you can read it, y equals the inverse tangent of x, looks like this graph but shifted, right? So this is now pi over 2 and minus pi over 2. And so we see that the limit as x approaches infinity of f of x, of the inverse tangent of x, is equal to pi over 2, and the limit as x approaches minus infinity of f of x is minus pi over 2. Good. So these are some kind of standard examples that you might run into. Good. Now, suppose and now we want to talk about a little bit something else. I wanted to mention definition. A function is said to be bounded if, let's take a look at a picture first. It's going to be bounded if the function is trapped between like two lines, right? So this would be like a number m, and we're saying that function f of x is bounded if the absolute value of f is trapped, is stuck between plus or minus m. So a function is said to be bounded if the absolute value of f of x is less than m for all x greater than some value. Oh, I guess we're going to take it to be all reals for all x. That'll make it easier to write. Good. Okay. So now the question is do all bounded functions have a horizontal asymptote? You might pause for a minute to think about it. Are you ready? The answer is no. For example, we could just take a look at the sine function. Is the sine function bounded? Yes, it's bounded by m equals 1, right? And so it also just stays oscillating forever, and so has no horizontal asymptote. Okay, good. All right. Now let's try some algebraic limits. We'll do one example. I think we have time for one more example here. Example: find all vertical and horizontal asymptotes. Let's see, this will be 3x squared minus x plus 1 divided by x squared minus 2. 1. Vertical asymptotes. Now for vertical asymptotes, remember that the limit as x approaches the a value has to be plus or minus infinity. And so we can look to see where the denominator is 0. Denominator is 0, but also check that the numerator is not. Because if the numerator is also 0, then you can't say that there's a vertical asymptote. So in this case, x is equal to plus or minus the square root of 2, And if you double check with the numerator, that would be 3 times 2 is 6 minus the square root of 2. Nope, that's not going to be 0. Okay, so these are the equations of our vertical asymptotes. Horizontal asymptotes. Now we're going to get a new technique now for finding a limit, and we're going to divide numerator and denominator by the highest power of x, in this case x squared. And let's see what we get if we do that. Let me write it down first. 3x squared minus x plus 1 divided by x squared minus 2, and divide by x squared, divide by x squared. Okay, so if we do that, feed that x squared through. Okay, and then you have 1 over minus 2 over x squared. Alright, so why did we do that? Because now if we take the limit as x approaches infinity, right, this is going to go to 0, right? That's the one we looked at before. And in fact, this one goes to 0, and this one goes to 0. And so what does that leave us with? It's just going to be 3 over 1. And so in this case, the limit is 3. And so our limit as x approaches infinity of f of x equals 3, so that is our horizontal asymptote. Good. We'll stop there and we'll go through some more examples of this technique. Divide numerator and denominator by x to the n. Alright, we'll see you then.